Okay, I hope I'm audible. So let's begin today's session. Welcome to your second discussion session on mechanical behavior of materials. I am Pragyandipta Mishra from Department of Applied Mechanics and Biomedical Engineering at IIT Madras. And today we'll be continuing our review on container mechanics by going through few more concepts. We'll be talking about Mohr circle, the concept of stream. We'll also be discussing about various moduli of elasticity. And finally, we'll be discussing about stress-strain relationships and solving a few problems on the same. So let's begin today's discussion. So first thing that we have to talk about today, of course, is Mohr circle. Now in the last class, if you remember, we had talked about how to determine the various values of stresses, principal stresses, etc., and so on and so forth, how to do transformations using equations directly. However, doing that was more of a mathematical way. Doing it by solving equations in some particular order, by solving matrices, etc. Right? There is another technique in which we can find the values of these stresses, whether it's for transformation purposes, whether it's principal stresses, or any other case that we need to solve. This technique is known as Mohr circle. So here, the transformation equation for plane stress is basically represented by a graphical form. And since this entire thing is in the form is of the geometry of this entire transformation is in the form of a circle, we can represent it as a circle. So if we have to describe Mohr circle in a few words, we can just say it's a technique by which transformation equation for plane stress just a second. Right. Yeah. Can be represented by a graphical form. Which in this case is a circle. Okay. Now, advantage of using this method is that you don't have to again go back and do numerical calculations. You don't have to remember big equations, and you won't have to like do matrix multiplication and all those things. You can just draw it and you can find the values directly. So, how does this essentially work? Let's understand that first. Now, if you remember from our last discussion, we had calculated the transformation for sigma x dash, sigma and tau x dash y dash, and sigma y dash in this form, right? So sigma x dash would be something like sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Similarly, if I want to write sigma y dash, it will just be negative of these two terms. These two terms will become negative. If I'll just mark it by red so that you can. Yeah, so these two will become negative, and this will be y dash. Okay, and if I want to write tau x dash y dash, this will be of the form negative of sigma x minus sigma y by 2, right, sin 2 theta plus tau xy sin cos 2 theta, right? This is what we remember from last class. Now, if we want to take, let's say that we want to represent this quantity, the quantity I am circling. Let's say I want to represent this quantity, the quantity I have enclosed in a yellow box. If I want to represent, I can represent it as an average of the stresses acting along the x and y directions, right? So I can put it as sigma x plus sigma y by 2, right? So it's an average of the stresses acting in the original plane, not in the transform plane, but in the original plane. So if I take this value to the left hand side and subtract it, I'll get sigma x dash minus sigma average to be equal to the remaining two terms, right? Sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Right? Now, if I do square of this, then I can write a square a. So if I want to do square of this, it will be something like sigma x dash minus sigma average the whole square is equal to, this is a plus b the whole square, right? So I can write a square, right, cos square 2 theta plus b square sin square 2 theta. Let me just write this square term a little smaller, okay, plus what? 2ab. So 2 into sigma x minus sigma y by 2 cos 2 theta tau xy sin 2 theta. Just a minute. So this is the square term for like equation 1. Let's take this as your equation 1 and this as equation. Now if I want to square equation 2 as well, I'll get tau x dash y dash square to be equal to, what is tau x dash y dash? Yeah. So again, this is a minus b the whole square, right? So a square plus b square minus 2ab. So if I rewrite that, sigma x minus sigma y by 2 the whole square sin square 2 theta plus tau xy square cos square 2 theta minus 2 times sigma x minus sigma y by 2 cos 2 theta sin 2 theta tau xy cos 2 theta. Now if I add these two equations, if I add this equation and this equation, what will happen? On the left hand side, I will have sigma x dash minus sigma average the whole square plus tau xy square. Sorry, tau x dash y dash square. So on right hand side, what is happening to this and this term? So let's take this term first. This term and this term are essentially having sigma x minus sigma y by 2 whole square as common, and then it will just be sin square 2 theta plus cos square 2 theta. Now we know from convention, as sin square 2 theta plus cos square 2 theta will be equal to 1. So that will just become equal to sigma x minus sigma y by 2 the whole square. Now similarly, the other term, if I represent it, let's say from another color, this term and this term is also of the same form, right? So these two terms are also of the same form. So I will again get only tau xy square left, and these two terms are exactly equal, the final two terms. So they will just cancel each other out. So this term and this term, the term I'm representing in green box, these two terms are just negative of each other, right? So they'll just cancel each other out. So finally we'll be left with only sigma x minus sigma y by 2 the whole square plus tau xy square. Right. Now, assuming that we know the values of stresses in the original coordinates. So we know sigma x, sigma y, and tau xy. We can say that the right hand side is a known quantity, while the left hand side is of the form of left hand side has the form of some unknown quantities and known quantities, right? So we know sigma average on the left hand side. Only this term is known in the left hand side, the one I've underlined, right? And sigma x dash and tau x dash y dash is unknown, right? So let's represent it in a different form so that we can understand what this looks like. So this will be x minus a the whole square plus y minus b the whole square is equal to r square. Now here a, b and r are known, right? B is equal to 0. A is equal to sigma average, which is again known. R is also sigma x minus sigma y by 2 whole square plus tau xy whole square, which is again known, right? So this is the equation of a circle, right? So the final equation is in the form of a circle, and we can say that your radius of the circle is equal to root of sigma x minus sigma y by 2 the whole square plus tau xy square, right? And your center of the circle, let's represent it as O, like O, the center of the circle is at a comma b or sigma average comma 0, right? I'll not write it as O, let's write it as C so that it should not be confused with 0. This is your center of the circle. This is your radius of circle. Right. So now we are clear as to why we are representing this in the graphical form as a circle, right? Because we have the entire equation in the form of in the form of x minus a square plus y minus b square is equal to r square, which is the form of a circle. So your if we represent your sigma x comma y and your tau xy in the xy plane in this manner, we can say that your sigma average, if it lies somewhere here, then your center of the circle will be on the x axis, right? And your entire circle will have the radius r, which is equal to this value, the value given in on top, and then you can draw a complete circle like that around it. Okay, this does not look like a circle, but okay, maybe I can use a tool to make it look like a circle. Yeah. Let's say this is the center. Okay, this is your C, and this is your R. So this is how your Mohr circle can be represented in geometrical format, in graphical form. Okay, and then you can do various calculations on it. So let's see what and all we can actually represent on a Mohr circle. Now, center and radius is something that you are now familiar with, right? So how would you go about drawing a Mohr circle? What would you do? First, you will try to find out the coordinates for for sigma x tau xy, sigma y tau xy again. So these are the coordinates of the points which are lying on the Mohr circle, right? Because anything that you are getting in the form of stress in one transformative coordinate. For instance, if say original plane has sigma x, sigma y, and tau xy as your stress values, then this will be a point on the Mohr circle, on the circle. This will be a point on the circle, and like this can be these individual quantities can be represented as a point on the circle. And again, if you also want to look at whatever transformed coordinates that you will have are also points on the circle. Okay, so every point on the circle, every point that you are looking at, 1, 2, 3, any point that you want to look at is some transformed coordinate of whatever initial guess that you started with. Okay. So for instance, if I say my sigma x is lying at some value, let's say I'm saying it lying here. Okay, let me represent it by different ink. Let's say my sigma x is lying here. So this point will represent sigma x. I'm sorry, if it is lying here on the x-axis. Sorry. Yeah. So it's lying on the x-axis sigma x, and then we know the tau xy value is lying somewhere here. So sigma x comma tau xy will lie somewhere here, and this will be a point on your Mohr circle. Similarly, if I say that my tau sigma y and tau xy also lie on the Mohr circle, so I can represent it by a point here. Say if this is my sigma y and this is my tau xy, so I can again represent it by a point on the circle where I can write sigma y tau xy. So to draw Mohr circle, first we have to determine these coordinates: sigma x, tau xy, sigma y, tau xy. So once we know these coordinates, we can just draw a line, and where it passes through the x-axis, because we know that b is equal to 0, right? For this circle here, b is equal to 0. We know this. So where it passes the x-axis, that's where your center will be lying, and then you can use that as the center, and then either this point, your point A or your point B, you can use to draw the entire circle. Once you know that, then any transformation you can do by considering that any change theta in the real world is equal to 2 theta in the Mohr circle. Okay, so this kind of transformation can be done very easily, very quickly in Mohr circle. However, you have to be very, very clear, geometrically clear, very, and you have to be also make sure that whatever graph you are drawing has to be to scale. If you are not drawing it to scale, if you are changing the scale somehow, you have to ensure that how you are keeping the scales. If you're not very clear with the scales, then you might run into some trouble. You'll run into some errors while doing the calculation. Okay. So point C has sigma average comma 0, which is your center of the circle. Point A, in this scenario, I have taken it as sigma x tau xy, but it might be other way around also. Okay, and point B is like sigma y tau xy. One important thing to keep in mind is what kind of sign convention you are doing while drawing Mohr circle. So generally, the sign convention that people use for Mohr circle is your tensile. So in normal stresses, tensile stress is taken as positive, compressive is taken as negative. While for shear stresses, clockwise is taken as positive, counterclockwise is taken as negative. Sorry. I'll just write CCW, that is counterclockwise, it is taken as negative. So this thing you have to keep in mind. Now you are free to change this sign convention, you are free to use your own sign convention, you can change it and you can use it however you want. But ensure that whenever you're changing sign convention, whatever you're using, you are true to that sign convention always. Don't keep switching in between the problem. Okay. So yeah, one more thing, I will just write it down so that it stays in mind. Theta in your real space is equal to 2 theta on Mohr circle. Okay. Not keep writing and writing. Okay. So this much is something that you have to remember in Mohr circle concept. Now, one more thing that I can, okay, yeah, a few more things that we can see on a Mohr circle is, let's say I have this as my sigma and tau. Let's say I have some Mohr circle here, right? This is my center C. Let's say I have some value here, some here, and I have drawn the Mohr circle in the original coordinates. Let's say this is my B. This time I will take this as sigma y tau xy, sigma x tau xy. Okay. So assuming that we have these coordinates, we can also find the values of what is the maximum shear stress, what is the maximum value of normal stress, minimum value of normal stress directly from Mohr circle. Now we know that the maximum and minimum value of normal stresses would represent the principal stresses as we had discussed in the last class, right? So your maximum value of normal stress would be here, right? Because this is the maximum sigma that the particular body can take, right? So this sigma value is your sigma 1. This point will represent sigma 2. So these are your principal stresses. Now why they have the principal stresses? Because they are lying on the x-axis, and x-axis has zero shear stress. So this point would ensure that you are only looking at principal stresses, and they are of course the maximum value of sigma that it can take, as you can see from the diagram itself. Now, if you want to see the maximum value of shear stress, you have to go either to the top, right, or to the bottom. It will be same thing. It will be the exact same value, whether you go to the top or whether you go to the bottom, because your center is lying on the x-axis. So top or bottom will have the exact same coordinate. So this value will give you your tau max, right? And this tau max, if you want to write it in equation form, will be something like sigma x minus sigma y by 2 the whole square plus tau xy the whole square, root of this. Now why am I able to write it in this fashion? Why am I able to write tau max as sigma x minus sigma y by 2 whole square plus tau xy whole square? Why am I able to write this equation? Because from point C to tau max, what is this? This is radius, right? This is r. And if C is at 0, then your tau max will be at r, right? The distance between C and tau max is the radius. So I can write tau max is equal to sigma x minus sigma y by 2 whole square plus tau xy whole square, the whole thing to the power 1 by 2 directly, because it's just the radius. Okay. So you can see that lot of equations that we have seen in the previous class can be proved using Mohr circle directly without even having to prove it mathematically. Okay. Now, one more thing is your sigma 1 and sigma 2 are basically two ends of the circle, right? So if I do sigma 1 minus sigma 2, what will I get? 2 times the radius, or sigma 1 by minus sigma 2 by 2 is equal to r. Okay, but r is also equal to tau max. So essentially your tau max is equal to sigma 1 minus sigma 2 by 2, right? So difference in principal stresses divided by 2 will give you tau max. So that is another thing that you can note from Mohr circle directly. There's a very good proof for this if you look at it from a numerical standpoint, that why sigma 1 minus sigma 2 by 2 is given you tau max. And I think most of you who have studied strength of materials, mechanics of materials, of any other related course would already be knowing this. But how does this come from Mohr circle? You can directly see it here, right? Because sigma 1 and sigma 2 are two ends of the circle. They are the diameters. Two opposite ends of the circle. They represent the diameter. So distance between them is the diameter. So divide by 2 will give us radius. But radius is also equal to the tau max value. Okay, so I think this much is sufficient for more circle. We'll now move on to uh, strains, concept of strain, and then we will look at how stress and strains are related and other things like model of elasticity and all. So strain. Now we discussed about strain in the last class, right? What exactly is strain? Now if you remember, what we talked about is strain is just a measure of deformation of a particular material. And just like stress, we can represent strain using two using both magnitude and direction. So it requires uh, two identity. So it is not enough for us to describe strain just like force with just direction. You also need uh, direction and the plane in which strain is acting. So it's also a tensor. Okay. Compared to that, okay. So stress, strain, etc. are known as tensors because you need two coordinates to describe stress value, two coordinates to describe strain values, right? While if you look at force, it's a vector because you need only one coordinate to describe force, just the direction. Okay. So what are the various kind of strains that we can see in any body? Just like stress, strain would be whatever kind of stress that we can see in a body, a similar kind of strain would always be present in the body. So if you're seeing strains in the x direction, y direction, we'll have normal strains, right? And normal strains again can be divided into two parts. One is known as lateral strain, which is along the direction of load. And then longitudinal strain. So these are the two types of normal strains that we will see. Which is perpendicular to the load. Okay. So for instance, if I have a body, something like this, I'll just draw 2D, but you can imagine it to be a 3D body, okay? So let's say I have a body like this, and I apply loads like this, some P, load P. So what will happen is, this thing will get elongated, right? The body will get elongated. Now the body is getting elongated in both the directions. So your strain value, the lateral strain value is essentially, oh, did I, oh sorry, I think I wrote it old. Sorry. Apologies. This thing I think I, lateral is perpendicular to the direction of load. Longitudinal is along the load. Okay. Yeah. Now it makes sense. Yeah. So if I'm applying a load along some direction, let's say here in this case we are applying it along x direction. So a longitudinal strain would be measured here. So this will be a longitudinal strain. While your lateral strain would be measured here. Let me just try to use different ink. Okay. Now, what is the importance of measuring longitudinal strain, lateral strain, etc.? There is an important concept in container mechanics known as Poisson's ratio. Okay. Now this Poisson's ratio is essentially represented by this symbol nu, and it is the ratio of the negative of lateral strain to longitudinal strain. Now, why is this important? Why would we want to find the ratio between lateral strain and longitudinal strain? Now, understand that any material will have an intrinsic property known as Poisson's ratio. Why? Because whenever we pull a material or push the material together, whether we apply tensile or compressive load, it just does not expand or contract in that one direction. What happens is, because of the expansion or contraction happening along one direction, the other directions will start contracting or expanding accordingly. So, for instance, if it is expanding along the x direction, you will see that there will be some sort of contraction along the other directions. Why? Because the atoms would start to reorient themselves along the x direction, and now because it is longer in the x direction, to conserve the volume, overall volume, the body will try to contract in the other directions and try to make sure that the total atomic structure does not get disoriented too much. Now, this is something that bodies normally do, and usually any type of material that we are looking at, be it metal, be it be it metal, be it non-metal, etc., or any type of material that we are looking into, you will usually see that within elastic range, if you are loading the material, whenever you will have an expansion along one direction, you will have contractions in the other directions. Now, this might not be true in some cases, which is why Poisson's ratio is a range. Okay, and to give you a clearer picture, the range is very well defined. It is between -1 to 0.5. Okay, which means that there are materials which are having negative Poisson's ratio. What would that mean is, if I am pulling the material, instead of contracting in the other directions, it's expanding in the other directions as well. Even though it's expanding along the x direction, it is still expanding along other directions as well. There are special materials which act like this, and there are materials which will have Poisson's ratio 0, which means that just pulling it in that direction will show no change along any other direction. Now, these are all special cases. Which only come into picture when we are dealing with those special material. However, for most metals or most structures that we look at, wherever we are looking for machines or construction, etc., for most material we'll have Poisson's ratio in the range of 0.2 to 0.4. Okay, so close to 0.3 is what you can assume Poisson's ratio to be. Okay. So essentially, why we are talking about Poisson's ratio? The material is trying to conserve its volume. The material is ensuring that if it is expanding along one direction, it is trying to contract along other direction so that the volume remains conserved. And then this value is a constant for a given material. Okay. So if we are measuring this Poisson's ratio value, you will have that value for that material throughout, unless you are mixing the material, making some alloy, etc., then the value will change. But if you just take the specific ideal material directly, the Poisson's ratio value will be one single value. Just like how you have modulus of elasticity, Poisson's ratio also will be one single value. Okay. Another special case for Poisson's ratio that you can remember if you want. Sorry. Is when it is 0.5. That is the maximum value of Poisson's ratio that it can take. So then in that case, you will have ideal plastic deformation. And the volume will continuously remain constant. Whenever it is not 0.5, there will be some change in volume as the material expands and contracts along the different directions. There will be still some change, But here the volume will remain continuously constant. Like there's no change in volume at all. Like there's no change at all in the value of volume. Okay, so volume remains constant throughout. Now, why this range we are looking at and how this -1 to 0.5 came about, we'll come back to it in some time. But for now, just remember this. Okay. Next concept. Just a second. Let me see if I missed something before I move on to the next concept. Yeah, I think that is okay. Okay, let's come to this now itself. Let me explain to you why having a Poisson's ratio for 0.5 is okay for us to like it is okay for us to say that the volume is going to remain constant throughout. Okay, why we are saying that the material is having a constant volume or the material is incompressible or rigid, right? So what will happen when a material is stressed along one direction, or because of that stress the material is compressing along other directions as well? So initially, let's say you have the volume equal to 1. Okay, your initial volume is equal to, let me just write it. The initial volume was equal to 1. Now, after we have applied strains along XX, YY, ZZ direction, what will be the new volume? The new volume would be equal to, let's say the dimension along X, Y, and Z, all three were 1 only. Okay, so it was 1 into 1 into 1. Okay, so 1 plus sigma XX plus, we are considering a cuboidal kind of volume. So you can just multiply X, Y, and Z directions. 1 plus epsilon YY and 1 plus epsilon ZZ. This is your new volume. So essentially, your change in volume would be equal to this new volume Vf minus Vi, which is your initial volume. Vi, and this is your Vf. Now, if I multiply epsilon xx with epsilon yy or epsilon yy with epsilon zz, what kind of quantity would I get? Understand that these changes in x, y, and z directions, epsilon xx, epsilon yy, and epsilon zz, whatever we are talking about, will be very small quantities. Okay, why? Because strain in the elastic regime would be very small compared to the size of the size of the system, size of the material, size of the specimen itself. So if the strain value is very high, which it would mean that the material would probably undergo plastic deformation, not just elastic deformation. So if you want to stay within the elastic regime, we usually assume that the strain is small. Okay, so let's say it is known as small strain approximation. Okay, you're assuming that the strain is very small. So if you are multiplying one small value with another small value, the resulting value would be even smaller, right? So sigma, so epsilon xx, epsilon yy, or epsilon yy into epsilon zz, if we do these multiplications, what would remain in the end is just 1 plus epsilon xx plus epsilon yy plus epsilon zz, and all other terms, and any other term that is equal to multiplication of epsilon xx with epsilon yy, or epsilon yy with epsilon zz, or epsilon xx with epsilon zz. So all other terms will be multiples of this, which will be very, very small. So assuming that those values are very close to 0 and we can take them as 0, your Vi is already 1. So your change in volume would just be equal to epsilon x plus epsilon y plus epsilon z. Zz, sorry, xx, yy and zz. Right. Now, what are we saying what are we trying to say if the volume remains constant? It would mean that your change in volume will be equal to 0, right? If the volume is constant, change in volume will be equal to 0. That is the claim of Poisson's ratio being equal to 0.5, right? Now, assuming that it's a, let me just add on the page. Assuming that it's a case where we have sigma x this is your equation for a general strain along x, y, or z direction, right? This is the general equation, right? So if your Poisson's ratio is equal to 0.5, what would happen in that case? And assuming that y and z direction are compressing together, they are compressing equally. So you're equal to sigma z, right? Assuming that the only stress acting on the body the only thing acting on the body is along the x direction. So your y and z directions, you will have almost similar values for things. So you can just take it as 2 times sigma y, right? So epsilon x would be equal to 1 by e sigma x plus 2 times Poisson's ratio times sigma y, right? Now what does this signify? Let's say that only sigma x is acting in this body. You will have epsilon x to be equal to sigma x by e, right? Now if sigma x and sigma y and sigma z were all acting together, just a second, I think there is something wrong here. Yeah, I think I made to be, yeah, this is the, yeah. Yeah, so this will be your value of epsilon xx. Your epsilon yy would be equal to 1 by e times sigma y minus 2 epsilon sigma xx. Sorry, there is no 2. Minus epsilon zz. Right. and your epsilon zz would be equal to 1 by E, same thing as epsilon yy. So you just assume this to be same. Now what is happening here is your epsilon sigma y and sigma z is equal to 0 in this case. So you will have epsilon xx to be equal to sigma x by E, right? Epsilon yy to be equal to negative times sigma xx, or also epsilon zz to be equal to that. Now what does this represent if you are having this kind of situation? In this case, now if your Poisson's ratio is equal to 0.5, right, your entire epsilon yy would become equal to sigma xx by 2e, right? Yeah, it's negative sign is there. Let's assume that sign is immaterial, right? So your epsilon yy and epsilon zz would essentially be change in epsilon yy change along epsilon zz would be half of the change along your epsilon xx, right? So if you add epsilon xx plus epsilon yy plus epsilon zz, what would we get? You'll get sigma x by E minus sigma sigma xx by 2e minus sigma xx by 2e, which is equal to 0. This is what we are getting, right? Finally. Now here, if you recall, just a few some time back, I saw that the change in volume was equal to epsilon xx plus epsilon yy plus epsilon zz. And if the volume remains constant, then your epsilon xx plus epsilon yy plus epsilon zz would be equal to 0. What did we get here again? We got that epsilon xx plus epsilon yy plus epsilon zz to be equal to 0. Therefore, if Poisson's ratio is equal to 0.5, your change in volume would be equal to 0. So there is no transverse, there is no volumetric expansion or contraction. That is what we were trying to prove here. Okay, I hope this is clear. I made a small error in the beginning, but yeah, like I think now it is clarified. This is supposed to be negative. Epsilon xx is equal to 1 by E sigma x minus sigma y plus sigma z by times the Poisson's ratio. Okay, I hope till here it's clear. Next concept that we'll be discussing about is true stress strain. True stress strain and engineering stress strain. Another very important quantity. Why? Because this basically tells us what kind of measurements we are doing in real life versus what kind of measurements are actually happening to a particular material. Okay, let me just check if I missed anything before that. No, this I covered. This is also fine. Yeah, okay. So, till date, whenever we study about any concepts in mechanics of solid or strength of materials, etc., whenever we study concepts there, we will be studying stress and strain in the form of engineering stress and strain. Okay. Why do we say that we are studying engineering stress or strain? Is because that is the quantity that is very easy for us to measure. Okay. So people usually tend to look at only engineering stress, engineering strain, and forget about what is the actual value of the true value of stress and strain. So F by A and your engineering strain, these are very common quantities that people will be using, right? Will be equal to change in length by original length. So let's represent original length as LO. Okay. True stress and engineering stress, true strain is different from engineering strain in this fashion. Here, your change in length and original length are not measured at your change in length is so in engineering strain your change in length is measured at every instant, but your original length is kept constant. However, in true strain, what we are doing is we are measuring the change in length with respect to the original length at every instant. Okay. So what is happening essentially is we are looking at whatever is the original length and looking at what is the change in length at that particular instant and integrating it above, like integrating over the total length. What this does is at every instantaneous change in length, we are also looking at what is the instantaneous change in the original length. Okay. So once we do this integration, we will end up with something like ln of Li by Lo, where Li is the instantaneous value of length. It's not the change in length, it's the instantaneous value of length at that particular instant, and Lo is your original length. So if I rewrite this, your Li by Lo will be like, I can just write this as Li is what? This is equal to Li minus Lo divided by Lo, right? So this will be equal to Li by Lo minus 1, right? So I can write this as 1 plus whatever is the value of engineering strain. So engineering strain, let's represent it by E. Okay, let's write it as E. While true strain, let's write it as epsilon. Okay. So this is your relation between true strain and engineering strain. Now similarly, we can find a relation between true stress and engineering stress, because engineering stress and strain are related by this relation. Sigma is equal to E times epsilon. I can write, E times small e. Actually, I don't want to write it as E and epsilon because there will be a lot of confusion later on. So I'll write it as ET and epsilon T and epsilon E, so that it's clearer. Both are actually epsilon only, both are strains only. So you can represent it as E and epsilon also, or epsilon E and epsilon T, whichever is clear for you, whichever is easier for you. I don't want you to confuse between the capital E and small e, so I'm just representing it as sigma, and so it has like E as your Young's modulus and your epsilon E as your engineering strain. So your true strain is equal to ln times 1 by E, right? So your true stress will be equal to what? It is equal to force by area, right? Just like how engineering stress is defined, but here area is instantaneous area. So that is equal to your sigma E times 1 plus E or epsilon. Now how did we get this sigma E times 1 plus epsilon E? Okay, look at it this way. Your true strain was ln of 1 plus E or ln of 1 plus epsilon E, right? Now your area is proportional to your change in length, right? I will not show you the full derivation. I would expect you to go back and look at this derivation and try to do it yourself. Think about it this way, okay? Your area is proportional to your change in length, right? So your AI is proportional to your Li, right? Or change in area is proportional to your change in length. Therefore, if I'm looking at stress and strain, how are they related? They are related by Hooke's law, right? Yeah, so your sigma E is equal to E times epsilon E. This is one relation. This is one relation. This is one relation. And then one more relation is your true stress. So let's represent this as sigma T. Is also equal to or is also proportional to, let's say, epsilon T. Right. So these three you can use to find the relation between true stress and engineering stress. So your final relation would be this. I have already given it to you, but I would want you to go back and derive it. I don't want to show it to you because then it will be like little bit like telling you everything. I would want you to go back and check it and derive it. If you are able to get it, it will be great. If not, we can discuss it later. Okay. So this is one thing which was left. Other than this, uh, yeah, one more thing is, of course, I think it was discussed in the lectures that is given on NPTEL. Your true strain, the reason why we are looking at true strain is because it's additive in nature, right? Engineering strain is not additive in nature, right? Because you can strain a material to twice its length. If you remember the example that they had given in NPTEL, if you strain the material to twice its length and then try to apply the same strain back to get it back to original length, you cannot do that, right? Because if you try to apply the exact same strain that you had applied in the negative direction, you will go back to zero. You will not go back to the original length. However, in true strain, you will go back to the exact same length. So that's why true strain is a much more easier concept to work on when we are looking at equations. However, while doing measurements, while doing while looking at it in real life, when we are looking at material behavior and all that, it becomes very difficult for us to operate in true strain, true stress paradigm, because you will have to measure quantities at every instant, which is a very tedious job. So what people do is they will measure quantities initially, and then they will only measure change in length, change in the dimensions at every instant, which is kind of okay to measure. Like it will be very easy for us to measure that comparatively, and then find your engineering stress and strain, which are related by your Hooke's law. Okay. Final topic that we have to discuss for today is concept of tensor, strain as a tensor, right? Like we discussed how strain is also a tensor just like stress. It requires two coordinates for it to be described completely. So you need to describe strain in the form of epsilon ij to be equal to epsilon xx, uh, epsilon xy, epsilon xz, epsilon xy, epsilon yy, epsilon yz, epsilon xz, epsilon yz, and epsilon zz. Again, the diagonal elements are your normal strains. So if I represent this, these are your normal strains. These are your shear strains, right? And just like stress, strain is also symmetric. So your value above the diagonals will be exactly equal to the values of the strains below the diagonals. So there are only 6 independent strain components. All right. So 6 independent strain components only you have to consider, and any transformation that we have studied for stress, okay, whatever we have looked at, whether it's in equation form that we did in the last class or using Mohr circle that we did in today's class, exact same transformation rules apply for strain as well. You don't have to again learn the same like some other procedure. It's the exact same thing. uh, Hooke's law will change for stress and strain. Okay, so in tensorial form, if you are trying to write Hooke's law, because stress is having two coordinates and strain is also having two coordinates, we have to write Hooke's law having four coordinates. Okay, stiffness tensor will have four coordinates, or it is of rank 4. Okay, okay. However, it is very difficult for us to uh, write everything in fourth rank, right? Because it will be very difficult for us to keep track of 1 1 2 2 3 3, all that, right? It will be very difficult for us to do that. So in order to make it easier for us, a different notation was invented by Voigt. Okay, so this is known as, just add Voigt notation. Now we don't have to go too deep into it. I just want to explain you why we need this and what is the advantage of this. Here, your sigma xx, sigma yy, sigma zz, okay, tau yz, tau xz, and tau xy are equal to your sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, and sigma 6. Now, how does this help us? How does this help us? What we have done is we have reduced the coordinates, the rank of the stress matrix from 2 to 1, right? Similarly, for strain also we can write epsilon xss, epsilon 1, epsilon 2, epsilon 3, epsilon 4, and so on. What has happened now is, because we are able to reduce the coordinate or the rank from 2 to 1 for stresses and strain, your rank for the stiffness matrixCijkl also reduces from 4 to 2, right? So it will become something like sigma I will be equal to Cij times epsilon j. So your entire coordinates are now manageable because it's in two coordinate system, it's manageable. Understand that this sigma 1, sigma 2, sigma 3, or epsilon 1, epsilon 2, epsilon 3, all those values are not principal stresses. Do not confuse these with principal stresses. They are not principal stresses. They are just notations given to stresses so that you can do calculations quicker and faster. Okay. Now, once you have written it in Voigt notation, it will be very easy for you. Okay. One more thing I can write here is, this is your stiffness matrix. Cij is your stiffness matrix, right? So you can write it in opposite form also, where epsilon I will be equal to Sij times sigma j. Right? Basically, what is Sij? It is just 1 by Cij, or Cij inverse of that matrix. Now this Sij is known as compliance matrix. Very, very useful again. While doing calculation, sometimes you might need to use compliance matrix over stiffness matrix, because your relations, stress strain relations, are usually defined in terms of epsilon equal to sigma x by E minus mu by E times sigma y minus mu by E times sigma z. So you are usually defining your epsilon to be equal to sigma x times something, right? Rather than defining sigma x is equal to epsilon times something. So compliance matrix becomes more useful when you are doing that. So therefore, compliance matrix also you should know. Okay. So finally, once you are able to write it in this form, you can write sigma 1, sigma 2, and so forth till sigma 6 to be equal to your Cij, which will be equal to C11, C12, like that, till C16. And C C12, C22, again till C26, and you can go on till C16, right? And you can keep going like this till C66. Okay, this is your stiffness matrix, and it is having 6 cross 6 components. Why? Because your stress has also 6 components, your strain has also 6 components, so this matrix will definitely have 6 cross 6 components, right? And this times epsilon. So epsilon 1, epsilon 2, so forth till epsilon 6. Okay. Now this notation will be very, very useful because you can do lot of calculations very quickly here, and you won't have to keep converting. Okay. One last thing that you can remember is these values of C11, C12, C13. Again, because stress and strain are symmetric, you will have symmetry here also. So essentially above this point, above the diagonal and below the diagonal elements will be equal. And based on specific material system that we are looking at, your values will be like will be either 0 or not 0. For instance, if you're looking at isotropic material has only two constants, C11 and C12. Okay, so you will essentially have C11, C12, and then C44. Why we will have C44? Because C44 will be equal to isotropic. Actually, let's say this is cubic material. Okay, this is a cubic material, because cubic material is a much more bigger family than isotropic. This is cubic material. Then if you want to look at isotropic material, it is just cubic material where C44 is equal to C11 minus C12 by 2. Okay, so you only need C11 and C12 for isotropic material. For cubic material, you need three constants, which is C11, C12, and C44. For hexagonal system, again, you will need 5 constants. You will need C11, C12, C13, C33, C44. And orthotropic material, similarly, you will need 9 constants: C11, C12, C13, C22, C23, C33, C44, C55, C66. So you don't have to remember all this. I'm just telling it to you. So depending on what material system you are looking at, all these values will either be 0 or non-zero. Okay, C11, C12, C44, all these will be either 0 or non-zero. But for all materials, C11 and C12 will always be present. Any other values like C44 or C33, C66, all these will be non-zero. Okay, so those values will basically depend on what kind of material system we are looking at. Therefore, your entire calculation will be very, very much easier for you to solve, because now you only have to deal with few components, and remaining all components in the matrix are just 0. So you don't have to do so many multiplications. You just have to do a few multiplications. So why we are defining isotropic materials so well is because they have only two constants that you need to define, right? You only need C11 and C12. Now this is equivalent to us defining our basic strength of material concepts, right? We usually use only two constants to define every material, right? Just E and U, right? E and Poisson's ratio. Young's modulus and Poisson's ratio, if you know, you're able to define everything about the material, right? That is because for isotropic material, these two are related. Okay, how they are related? They are related by a constant known as Lami's constant. Okay, so assuming that we are representing your C11, sorry, your C12 as equal to lambda. Now this lambda is Lami's constant, and your C11, C11 to be equal to 2 mu plus lambda. Okay, because your C44 is equal to mu. Okay, so it is equal to C11 minus C12 by 2. Again, this is something that you don't have to remember. Okay, It is just something that I'm telling you for your, like, in case you are going into advanced studies within the same course, you might need this. So your C44 is equal to mu or G. Okay, mu or G. G is what? G is your shear modulus. So what we now have is your shear modulus G is equal to your C44 in isotropic materials or in cubic materials as well. Actually, it's the same, but we are only talking about isotropic. And then your C1 will be equal to 2 times G plus lambda. Okay, lambda is equal to C12. Okay, so using this, you can also derive the relation between your various modulus of elasticity. For instance, if I want to know the relation between shear modulus and E, I can write G is equal to E divided by 1 plus 2 nu. Right, this is one relation. Similarly, if I want to know the relation between bulk modulus and modulus of elasticity, I can write K to be equal to E divided by 1 minus 3 times, sorry, yeah. Wait, one second. Wait a minute. It is 3 times 1 plus. Just a second, let me check my notes. Yeah, so three divide by 3, 1 minus 2. Yeah. So this is your relation between uh, bulk modulus and your elastic modulus. Now, one important thing that you have to note is that all these relations are based out of some derivation. For instance, if you want to look at bulk modulus, you will see that okay, delta V will be equal to your change, like your change in volume, like I've already derived, is equal to epsilon x plus epsilon y plus epsilon z, right? So your change in volume, your epsilon x is something like 1 by E times sigma x minus mu times sigma y plus sigma z. Similarly, epsilon y and epsilon zz also we can write, right? Similarly, we can write these two also. So if I substitute and I try to solve, your change in volume will be equal to your 1 minus 2 times mu divided by E into epsilon x, sorry, sigma x plus sigma y plus sigma z, if you substitute and solve, right? So your change in volume by original volume is equal to strain, right? And if I okay, this is your change in volume. Your change in volume by original volume is strain, and then volumetric strain, and then your volumetric stress. Let's say that it's P because it's pressure, right? Okay, not this P. Yeah, this is equal to K times volumetric strain. So if we are assuming that your sigma x, sigma y, and sigma z, because it's hydrostatic state of stress. by 3 is equal to sigma m. Okay, because it's a hydrostatic state of stress, then I can rewrite this equation as change in volume to be equal to 1 minus 2 nu by E, sorry, by 3 3 times sigma m. Yeah, this is the correct. Right. So I can rewrite it in this fashion. So your K essentially becomes equal to sigma m divided by 1 minus 2 nu by E, right, times 3 sigma m. Correct? I hope this much is clear. This is, sorry, this is not change in volume. Okay, by original volume. This is change in volume by original volume. There's also change in volume by original volume. Yeah. So this is your K, and so if I say that this is sigma m, so I can rewrite this in this fashion, and sigma m will get cancelled. So finally I will have E divided by 3 times 1 minus 2 E. Yes. So this is the correct relation between bulk modulus and modulus of elasticity, Young's modulus. So you can see that all these derivations have been proven based off of some calculations that have been done over some time. Just a second. Yeah, on my screen was not showing. Yeah. So essentially, if you're trying to find some relation between some quantities, between the modulus of elasticity, between bulk modulus, etc., we can derive it directly if you're not able to recall the equations. Okay, so you can derive it quickly using this formula. Similarly, for shear modulus and Young's modulus, you can use this Lame's constant and you can try to derive the relation very quickly. Okay. One more thing I think that was left was plane stress and plane strain condition. Yes. So one last thing before we move on to problems. What is plane stress and plane strain condition? Now, plane stress essentially means stress is acting along a particular plane. So it's a 2D state of stress, which means that the stress along the third direction, let's say sigma z is your third direction, is equal to 0. Or let's write it as sigma 3, okay, is equal to 0. So you will have only epsilon, you will have sigma 1 and sigma 2 present. Now we know that your epsilon 1 will be equal to what? 1 by E times sigma 1 minus mu times sigma 2, right? Because sigma 3 is anyway equal to 0. So that is your one relation. The other relation that we will have is epsilon 2 will be equal to similar form sigma 2 minus mu times sigma 1. And finally your epsilon 3 will be equal to 1 by E times negative of mu sigma 1 plus sigma 2. Now if we flip this around and we rewrite this in terms of stresses instead of just writing it in terms of strain, if you rewrite this, you will get sigma 1 to be equal to E divided by 1 minus square times epsilon 1 plus mu times epsilon 2. Again, you don't have to do it. You don't have to remember this equation, sigma 1 and sigma 2. You can just remember the basic equations. You can get your thing, but you have to understand what plane stress and plane strain conditions mean. Plane stress would mean that your stress is acting only along two directions, x and y. Okay, you will have sigma x, sigma y, sigma or tau xy. You will not have sigma z, any component of sigma z. Okay, And similarly, I can write also sigma 2. So I'll just not write it. Just the exact same thing. So plane strain, final thing. Here you will have strain acting along only two directions, similar to plane stress, where sigma z was equal to 0. Here epsilon z or epsilon x or epsilon some one particular direction, your epsilon will be 0. So all the values of strain along those directions will be equal to 0. So your epsilon z will be equal to 0, and then you will have epsilon 1 to be equal to, or epsilon 3, let's say, because let's not write it as xyz, because you should not assume that it's only along z direction or only along x direction, etc. Let's assume that it's along direction 3. Okay. 1 by E sigma. Yeah, sorry. So before that, we can find this. So your 1 by E epsilon 3 minus 1 plus sigma 2 is equal to 0. Right. So essentially, your epsilon 3, so sigma 3 is equal to mu times sigma 1 plus sigma 2. So this is one relation that will be there for all plane stress condition, and then using that you can find epsilon 1 to be equal to 1 by E. I'll just write one of them. So epsilon 1 and epsilon 2 both will be equal. So we just flipped sigma 1 and sigma 2. So this will be 1 by E times 1 minus mu square times sigma 1 minus mu times 1 plus mu times sigma 2. Again, you don't have to remember this equation. Okay. Similarly, you can write epsilon 2. Okay. Just similarly, you can write. You don't have to remember these equations. You have to just remember how or what condition we are looking at it. And then you can just choose your plane, just the regular equations, the Hooke's law equation that we are using, and you can solve any problem using that. Okay. So with that, we will come to the end of discussions for this. We'll take a 1 minute, 2 minute break, and then we'll come back to your problems on various concepts in this subject. So just give me 1 or 2 minutes. We'll come back. Okay. Let's get back to the problems. Just give me a second. Let me just sort this out. Yeah, okay. So moving on to the practice problems. Let me just okay. The first question says, in a physical body, what is the angle between plane of maximum shear and plane of no shear stress? So, what is the plane of maximum shear and what is the plane of no shear?
It
I'm
will
sorry?
be 45 degrees, sir.
Yes. Why? Because what is the plane of no shear stress?
So the maximum principal plane, like the principal
Yeah,
plane.
principal plane. Not just maximum. Even the minimum principal plane might also be plane of no shear stress. Just the plane of principal, like planes having principal stresses are known as plane of no shear stress. So the answer would be 45 degree. So now in the next question, they have given us 4 different Mohr circles, and they are asking us which of these are actually not a representation for a 2D state of stress. Among these 4, I hope you can see the question clearly. Which among these are not a representation?
Sir, I think the one with means for not a representation for 2D stress.
Yes.
Sir, can you mark it as A, B, C, D?
Yeah. So this is your A, this is your B, this is your C, and this is your D.
Sir, I think A.
A. Why?
Sir, because it is like pure shear stress.
But why would you say that this is not a possible configuration? Okay. The answer is not A. I'll give you that. I'll give you one more hint. What is if we represent, if you remember, we had discussed about Mohr circle. What is the one thing that we noted in Mohr circle when we represented it in the form of a circle? We had something like this, right? X minus A the whole square plus y minus b the whole square is equal to r square, right? The general equation for circle. What did we note in the circle?
Um, Means sir, like this
We noted that b was equal to 0, right? If you remember.
yeah, yes sir, yeah.
So if b is equal to 0, what does that mean? Your center will always lie on which axis?
X-axis.
Yes. So in these options, which of these case will you not have a center lying on x-axis?
So only option B.
Yes. So that is the correct thing. That is the option that is not possible for the case of Mohr circle, right? Why option A is okay? Because I'll clarify. Because you chose option A. Why option A is correct is because let's assume that you have a state of stress where you have sigma x, sigma y, both to be equal to one single value, single state. Sorry, same value, but this is, let's say, compressive. Okay, what would happen in that case? Your one sigma will lie here, one will lie here. Both are same, exact same values, right?
Yes sir.
And then when you draw the circle, what will you get? You will get exact this circle only for this state of stress, the one which I have drawn here at the bottom. If you draw the Mohr circle, what will you get? You
Sir,
get
I
this.
think the radius will be 0.
What will be 0?
The radius,
Why would the radius be 0?
not 0 sir, means like the formula of radius was like the sigma xx minus sigma yy by 2 the whole square. So
Right.
that term will get 0 and then we will be only left with tau xy.
It is sigma x minus sigma y by 2 the whole square, right? What is sigma x equal to? Sigma y equal to minus sigma, right?
Yeah.
This is what you're getting.
Yes sir, it will be, yeah.
So then it will become 2 sigma by 2.
Yes sir.
It is not 0, right? It is non zero.
Yeah, so that sigma y was with the negative
So
sign.
because I chose tensile in one direction and compressive in the other direction, your
Yes sir.
sigmas added up rather than getting subtracted for the radius. So you will get this option A as your Mohr circle in that case. So option A is also possible scenario for Mohr circle. Okay. So let's move on to question number 3. They are telling the state of stress at a particular point M in 2D loading is such that the Mohr circle point is a point located at 150 MPa on the positive normal stress axis. Okay. Determine the maximum and minimum principal stress values for the above stated conditions. So they are saying for a particular case, your Mohr circle is just a point M located at 150 MPa on the x-axis. Okay, this is your Mohr circle, just a point located at 150 MPa on the positive normal stress axis. So what can we say about the maximum and minimum principal stress values for the above stated condition? Any idea? This is what you were thinking the previous question to be, if you think about it. Your Mohr circle is
Yes,
just a point. Yeah, go
yeah.
ahead.
Sir, so I think the means the maximum and the minimum principal stress, like they will match with each other.
Okay. So you will say, so what will be the value of maximum and minimum principal stresses? If they're matching, what is the value?
So then, so no, like in this case, the radius is 0. So
So the
then,
only possible stress value is what?
yes, sir.
The only possible stress value in that case is what? If the radius is 0.
So like it will be 0 only.
No. Stress is not dependent on radius, right?
Yeah, yes, sir, yes, sir.
Stress is not dependent on radius. Stress is dependent on the coordinates of each point on the circle, right? Now here the circle is only one point, which means that that point is itself what? That point itself is the principal stress, right?
Yes, sir.
So both the values of principal stresses will be 150 MPa only. You want to see a mathematical verification of this? Why I'm saying that? Okay, I'll show it to you because you should not be confused why I'm saying this. We are agreeing from a Mohr circle standpoint, right? M is equal to 150, so only point we are seeing on the circle is 150. So that point itself should be the principal stresses, right? Now, but if you want to look at it from a mathematical point of view, think about it. Your R is equal to what? Sigma x minus sigma y by 2 the whole square plus tau xy square whole to the power 1 by 2. Now your R is equal to 0, correct? Which means that your sigma x minus sigma y by 2 is equal to 0 and your tau xy is equal to 0, right? Which would imply that sigma x is equal to sigma y at all points, right? Moreover, if I substitute it back in this R equation, I can write R equal to sigma x minus sigma y by 2, right? So R, since sigma x and sigma y are 0, R is equal to 0. So basically, we are looking at a roundabout thing. Sigma in the x direction, sigma in the y direction, both are equal, right? They are not equal and opposite, they are equal. So they both will assume the same value, which is 150 MPa. Therefore, that 150 MPa is the only possible value of stress in x or in y direction, and that is the maximum possible value because that is the only possible value. Okay, so that's why both will have 150 MPa only. Okay, next question. Which statement is incorrect for ideal plastic deformation? Sum of plastic strain is 0. No work hardening during plastic deformation. Poisson's ratio is 0.5 and volume of the material changes after deformation. Now, if you remember, we discussed about ideal plastic deformation, right? We discussed what happens in ideal plastic deformation.
So that volumetric strain is 0.
Which is incorrect. So you are saying A, B, C, or D?
So D, sir, D.
D you are saying is incorrect. So you are saying sum of plastic strain is equal to 0, which is correct. Epsilon x plus epsilon y plus epsilon z was equal to 0, right? We saw it.
Yes, sir.
Poisson's ratio was equal to 0.5. We saw that. Option number C is also correct. No work hardening during plastic deformation. So work hardening is a concept that we will study going further, but it just means that when you're applying plastic deformation, the material will not undergo any like change in property. The property will remain almost same. So it will just flow. There will be only flow. There will be no hardening per se. So that concept is again like just saying that no work hardening happening during plastic deformation again is a very loose way to say that something will not happen. It is not related to ideal plastic deformation at all. But the final thing, volume of the material changes after deformation is something that is completely wrong. We saw that volume remains constant for ideal plastic deformation. So that is the correct option. Okay. Next question. The strain in the radius and height of a cylinder is x and y. Then the volumetric strain is given by what? So this is a problem that we'll have to get down and solve. So they have given us strain values as x and y. So they're asking us what is the volumetric strain. Let's try doing it. So assuming that radius of the cylinder is r and your height is h for cylinder, then your strain in radius will be equal to dr by r, right? Change in radius by original radius, which is equal to your x, and your strain in height, which is equal to change in height divided by original height, which is equal to your y, right? That is what is given. The volumetric strain for this change in volume by original volume, that is equal to what? Pi r square h, right, is your volume for a cylinder. So this will be pi r square. So r plus dr. Actually,
So actually the square term will be like 2 dr by r.
correct. Because why will we say that it is 2 dr, 2 times r times 2 r dr? Why are we saying that?
So like the differentiation of x to the power n is like nx to the power n minus 1. So
Exactly. So if volume is equal to pi r square h, change in volume will be equal to pi times, like derivative of volume will be equal to.
sir, why will like pi come? Pi is a constant, no?
I'm sorry.
Sir, like why will pi come? Pi is a constant.
Pi is a constant, but if you do derivative, constants will just come outside, right? So assuming, so if you're doing dv,
Okay, sir. Okay,
this
sir.
is just
So
a general derivative, right? So
yeah,
pi
yes,
times,
yes, yes.
pi times h into 2r dr. So the first derivating r with respect, like first we are finding the derivative of r square, then we'll find the derivative of h, right? Pi r square dh, correct? So your dv will be pi times h 2r dr plus pi r square dh. I hope you agree. And the denominator we'll have pi r square h. Pi will get cancelled. What else is common? One of the r will get cancelled. So if I look at dv by v, it will be equal to 2 times one of the r's get cancelled, so h dr plus on this side here r and h will get cancelled. Okay, actually I can just remove h also. So 2 times dr by r plus dh by h. Correct? This is something that you have to find. So what is dr by r? That is x. So 2x plus dh by h is y. So 2x plus y is your option. So it should be this option. Correct? Any doubt?
No, sir.
Okay. Next question. They are telling us the Poisson's ratio for a material when bulk modulus is twice the modulus of elasticity. So bulk modulus is twice the modulus of elasticity. K is equal to 2 times E is what they have given. They are asking us what is the Poisson's ratio for the particular material. Now we know the relationship between bulk modulus and modulus of elasticity. K is equal to E divided by 3 times 1 minus 2 mu. Right? That is the relation. Now K is equal to 2 times E. If I substitute 2E equal to E divided by 3 times 1 minus 2 mu. E and E will get cancelled. So you have 6 times 1 minus 2 mu equal to 1. Right? Or solving it further, 1 minus 2 mu equal to 1 by 6, which is equal to 2 mu 1 minus correct? Any questions? Any doubt? How we got this? Straightforward, right? If you know the relation between your modulus of elasticity and bulk modulus. So I would recommend remembering only two of them, just elasticity, bulk modulus, and Poisson's ratio, and then modulus of elasticity, shear modulus, and bulk and Poisson's ratio. The other two you can derive quickly. Any other relation from there you can derive very quickly. So only these two, if you remember, it is sufficient. Okay. Next question, they are asking, what will be the shear modulus in megapascals for a material? And they have given us the properties. Bulk modulus is equal to 1.6 times 10 to the power 11 pascals. Poisson's ratio is 0.3. They're asking a shear modulus. So we don't know the relation between bulk modulus and shear modulus directly. Assuming that we don't know, what we can do is we can find E from K and then G from E. One plus two, right? Yeah. Okay. Using this, we can directly, let me just check. I'm not a little bit confused. Yeah, it's correct. 1 plus 20. Using these two relations, we can find what is the value of G directly. Or if you want to know what is the relationship between G and K, G is equal to 3 times 1 minus 2 mu divided by 2 times 1 plus 1 plus mu times K. That is a direct relation if you want to directly use it. But you don't need to. You can just use the relation that these two relations and you can directly find the value. Okay. So if you substitute for in the above equation what is the value, you will get your final answer for bulk modulus in megapascal. So these are given in megapascal to be 75, 73. Yeah. So 1 second. Let me just check my calculator. Yeah, 73. 73, 846 is the final answer. Did you try it? Did you get the same answer?
Yes, sir.
Okay. So next question. Okay. Again, they have given us 4 statements. They are asking us which of these is incorrect. True strain is additive and subtractive in nature. I think that is correct. Shear stress is 0 along the principal plane. Again, that is correct. Pure shear is a special case of plane stress condition. What happens in pure shear case? There is only shear stress acting, and plane stress condition. What is the scenario that we see in plane stress condition? We'll see that stress along one direction does not happen.
Yes, sir.
But if stress is not happening along a particular direction, can pure shear still happen? Think about it. Let's say we are having now if I remove sigma x and sigma y, only pure shear, only tau xy is there. Is it still plane stress?
Yes, sir, it
Yes.
is, but sir, pure shear is not here, right?
What is pure shear then?
So pure shear means like there is no normal stresses acting on.
That's what. So if I remove sigma x and sigma y, only this is acting. Is this pure shear?
Yes, sir.
So is this plane stress?
No, sir.
Why?
So because like in plane stress we have like a stress along one of the direction as 0, but for in other 2 directions the normal stresses can exist.
Correct. But they can exist, right? They need not exist. The condition for plane stress is one of the directions. Let's assume sigma z here to be equal to 0, right? But it does not say anything about sigma x and sigma y, right?
Yeah, yes, sir.
So pure shear is still possible, right? Because you are still not saying anything about the third direction. Third direction is still 0. What happens in the first and second direction is again immaterial of what is happening, because plane stress condition is only talking about third direction being 0. It is not talking anything about first and second direction. So you can have anything in the first and second direction. So this is also correct. But the last statement, engineering strain is additive and subtractive. Is it correct or incorrect? If you remember in NPTEL video, sir had talked about an example where engineering strain was shown to be non-additive. Right? If you strain a material to like double its length, your strain is what? Strain is equal to 1, right? And then if you just put -1 strain from this double length, if you put -1 strain, it will come back to 0. It will not come back to half. So you need to put half, right? So it is not additive directly.
Yes, sir. Like true strain is additive, but engineering strain can be
Strain is
more.
not additive. Yes. So this is the correct option. Next question. Consider a 2D stress state where stress along x and y axis are 20 megapascals and 10 megapascals respectively. Shear stress along x and xy plane is 6 MPa. Poisson's ratio is 0.3, Young's modulus is 10 GPa. Find maximum shear stress. They have asked us to find maximum shear stress. So they have given us sigma x to be equal to 20 MPa, sigma y to be equal to 10 MPa, tau xy is given as 6 MPa, and E and Poisson's ratio 0.3, E is 10 GPa. They have asked us to find maximum shear stress in MPa. Okay. Now, in this question, what are the information that we need to find this maximum shear stress? What do we need? Okay, what is the equation for maximum shear stress? How do we find the maximum shear stress? Let's draw a Mohr circle. I think we just discussed it in the class. Let's say this is your Mohr circle. Which point is your maximum shear stress? This, right? So your value of maximum shear stress would be what? Equal to what? If this is your center.
Sir, I could not hear you. My signal got disturbed.
Okay, yeah, I'll repeat. So they have given us this information, sigma x, sigma y, tau xy. They have given us Poisson's ratio and modulus of elasticity. They are asking us to find maximum value of tau xy or maximum shear stress value. How do we find maximum shear stress value? In Mohr circle, we discussed one very important concept, right? Your maximum shear stress would lie where?
Sir, on the plane that a particular angle, sir, that 2 theta is like that.
Is it? But on Mohr circle, where will it lie? Where will be your maximum value of tau? On the circle, where will it lie? On the circle, it will lie at the topmost position or the bottommost position, right? That's where tau will be maximum.
Like the two ends of any diameter, sir,
Any diameter?
or like the diameter.
The diameter that is parallel to the y-axis, right?
Yeah, yes, sir, yes, sir.
This diameter, right? If it lies on this diameter, then it will be the maximum, right? So
yes.
So what is this equal to?
It is
From
the radius.
It is the radius. So your tau xy max will be equal to radius, right? And what is the radius of a Mohr circle? Sigma x minus sigma y by 2 square plus tau xy square, the whole root, right? Now in this question, why have they given us Poisson's ratio and modulus of elasticity then? If they want us to find only maximum shear stress, why did they give us that?
I don't know, sir. I'm not able to recollect.
Do you think we need like Poisson's ratio and modulus of elasticity? Does it seem like we need it?
Sir, like in the formula, it is not required.
Exactly, right? So many a times in questions you will get extra information which are not required. Sometimes when you look at the question and you will feel, oh, they have given this also. Why have they given this? You will not find any use for it. So therefore there is no need for that thing. It's just given extra. Okay. So you don't have to worry about it. Okay. So only this sigma x, sigma y, and tau xy is enough for you to find your maximum value of shear stress. So if I substitute and find out, you can also do the calculation with me. I will do the calculation.
So
Yeah.
So I have one doubt in that cylinder one question, the volumetric restraint of a cylinder.
Okay.
Um, so can you like just go through? Yeah.
This
Sir,
one.
yeah. Sir, suppose like if we are stretching it along the height, then it's like the circumferential direction will reduce, no? So
Okay.
So like, sir, why are we adding this? Uh, like if one strain is additive, then the other one must be subtractive.
True. That is correct. Here we are not considering the signs. See, when I'm writing dr by r and dh by h, I'm not talking about the signs. I'm only talking about the mathematical equivalent. The summation comes because of maths. Like in maths, it will be plus. But if if dr by r is positive, then you are right. Like if for example, if I'm stretching it along the height, if dh by h is positive, then dr by r will be negative. So your positive and negatives will come here. If this is positive, this will be negative, and vice versa.
Okay, sir, understood, sir.
You got it? Yeah. Now that is a good question. Good that you clarified, so that should not carry this doubt late to late class. Okay. So I got my answer. I got 7.8 something. So 7.81 is your answer, I think. Check if you get the same answer. I mean, if you don't get the same answer, then let me know. I think that is the correct answer. Okay. I think we are almost out of time. We'll just do this next question and we will end it. I had some more question, but it's okay. We'll finish with this question. So they have asked in the above question, the same question that we have seen above, what is the value of principal strain? Okay. So they have given us they have given us stress values, they have given us maximum shear stress, etc., etc. What is the value of principal strain? They are asking. Okay. How would we find principal strain? Let's just discuss it and then we will end it. We will not sit and calculate it because it will take some time to calculate. How would we find principal strains? Epsilon 1 and epsilon 2. How would I find it?
So for that, like we would require this value of Poisson's ratio and elastic modulus.
Exactly. So here we will need your Poisson's ratio and elastic modulus. So what is the value of principal stresses? We can write 1 by E times sigma 1 minus this, right? And this I can write it as 1 by E times sigma 2 minus Poisson's ratio times sigma 1, right? So first I'll find sigma 1 and sigma 2 for these two cases. And then I can find epsilon 1 and epsilon 2, right?
Yes, sir.
So again, I don't think we'll have to, we can sit, we need to sit and do it. I hope everyone knows how to find principal stresses and then again find epsilon 1 and epsilon 2 from there. So calculate that. Finally, you will get some answer, which will be one of the options among these. Okay. With that, we will end today's discussion. I hope everyone is clear on all the concepts of continuum mechanics that we have discussed till now. Any doubts, anything else, we can discuss in the subsequent classes. From subsequent classes, we'll not be reviewing any more continuum mechanics concepts. We'll be reviewing them only as and when we require them. We won't need any more concepts directly. So whenever we will come back to continuum mechanics, we will only be coming back and reviewing it as and when those concepts come up in different topics that we discuss. So with that, I would like to end today's class. I thank everyone for joining in, and any any further discussion, any further doubts, we can move it to the next class, which will be happening on next Tuesday again at 6 p.m. So till that time, thank you everyone.